Let me start with amino acids. Check out this. Amino acid is when you have an amine group and an acid group. And mostly all naturally occurring amino acids are alpha amino acids. Okay. Now within these alpha amino acids, you need to understand one thing. When you write the Fisher projection on that, so if I put this in terms of priority basis, so this should be 1, 2, 3, and 4. So this is the priority which you will get. Okay. So on the basis of this priority, what we can say that 1, 2, 3, which is going clockwise, which means it is S configuration. Okay. And for a single chiral center here, most of the alpha amino acids are only S configured. Okay. And they will be levorotatory. Levorotatory. So most of the naturally occurring amino acids are levorotatory. A lot of JEE questions have been asked on this. All you need to check out if it is natural or not. How do we check out? Just check out the configuration on the alpha position of amino acids here. If that matches with the lever rotation, that has to be natural amino acid. Okay. And now, when it comes to categorization of amino acids, there are three ways by which we can categorize. First is neutral amino acid, acidic amino acid, and then basic amino acid. Neutral amino acids are those where you have number of COH groups and NH2 groups exactly equal. For example, here, if you have one COOH, one NH2 group, that means it is a neutral amino acid. While if you have number of COH groups more than number of NH2 groups, we call it as acidic amino acid. And if NH2 dominates over COH, we call it as basic amino acid. Done. There are three types of amino acids. Keep that in mind. Next, except the glycine part, all the amino acids are chiral in nature. Now, what is a glycine molecule means? Glycine is like this, where you have, COH here. Go back here. How did I write down? No, NH2 here, H here, and H here. So normally this is supposed to be an R group. If that R group is H only, then this is called glycine. And in that case, this does not remain as a chiral center anymore. Okay, so that is the glycine part. And next, amino acids can be classified as another two kinds. One is essential amino acid, the other one is non-essential amino acids. And see, if the amino acids which body cannot produce on its own, we call it as the essential amino acids. And if amino acids which body can produce on its own, then we call it as non-essential amino acids. Okay. So you can see this is the general formula of amino acids. Okay. So on this general formula, if I just simply change the term R with some new molecule, you would be able to find various amino acids here. Got it? So starting with C. First five, you remember it like a set, everybody. This is, and unfortunately, you have to remember all of this by structure. Okay. If the R is H only, we call it as glycine. It is a chiral molecule. There are two symbols that we can write. One is a 3-letter symbol. The other one is a code symbol, which is 1-letter symbol. So the 3-letter symbol is GLY and this is G. Alanine is CH3. So that is ALA and A. Valine, which is isopropyl group connected here. This should be isopropyl group. That is VAL and V. Then leucine. Leucine is isobutyl group. So that is leucine and L. Then you have secondary butyl. Secondary butyl is isoleucine. So you can see there is little confusion. Although this is isobutyl, it is called leucine. This is second degree, what is called as isoleucine. So ILE or I. So have you noticed this, that whatever be the first alphabet, that is the same code name they got. Okay, that's why the first five, are important and easy to remember. Okay, so So in that case, it will be called as, so easy to remember, Gavli, Gavli, Gavli. And then you see sixth and seventh is also easy to remember. Arginine. Arginine is basically an extra NH2 group having, right? So this is a guanide form. Guanine form. Have you remembered? I'm sure you remember the guanine form. So this is a guanine form with extra three carbons. That's it. So it is like a propyl guanine. That's it. So if the propyl guanidine. If the propyl guanidine is present, that is arginine, ARG and R, not A, it is R. And similarly, if you have four carbonants, one extra NH2, it is a basic amino acid which is called as lysine and K. Okay, lysine is represented as K. Clear? Other four are also easy to remember. So far, what did we learn, everybody? Neutral amino acid, basic amino acid. Then you see, next is acidic amino acids. There are only two acidic amino acids. One is glutamic acid, the other one is aspartic acid. If you have a overall propanoic acid as a substituent, that is called glutamic acid, GLU and E. Glutamic acid is E. Next, aspartic acid. If it is only ethanoic acid connected, okay, then it is ASP and D. ASP and D. These ED are difficult to remember. I know that it will take some time, correct? But slowly first learn the structures. Then if you simply turn this glutamic acid into an amide form, that is called glutamine, and aspartic acid, if you convert into an amide form, it is called asparagine. So it is GLN and ASN. So same GLU become GLN, ASP become ASN, and GLN is Q, ASN is N. So these are also another neutral amino acids. Then comes few different amino acids, that includes threonine and serine. Both of these are OH group linked ones. So one is ethyl, one is methyl. Methanol and ethanol. So threonine, THR and T, serine, S and S. Next is cysteine. Cysteine is with SH and methionine is with SCH3. That's it. So this is cysteine, CSS and C, and methionine, MET and M. And last four comes phenylalanine, which is like this. Okay, basically same alanine but phenyl substitution. So it is called phenylalanine. So FEH. So because it is sounding more of Fa, so remember F. Next, tyrosine. So tyrosine is like a phenol group within CH2. So TRY and Y. Tryptophan. Tryptophan is a very different group here. So it will have an pyrrole and benzene ring connected with a CH2 end. So tryptophan and W. Histidine. Histidine is very specific. You will have indole connection. This is indole ring. Indole connected with CH2, that is histidine. HIS and H. Only one amino acid which is 2 degree is proline. Proline is the only amino acid which is actually a 2 degree amino acid. So that is proline, PRO, and it is represented as P. Clear? So this is how much you need to know from these cases. Okay. I suppose this is clear, right? Now see, what is the main existence of amino acids? Okay. See, amino acid has both acid and base group present on it. That's why internally acid-base reaction can happen. That means this nitrogen's lone pair can take H plus and convert into the dianion. Um, as a charged ion, which we call it as a Zwitter ion. Dianion, sorry, dipolar. My mistake. Dipolar. Dipolar molecule. So dipolar molecule, as in it will have polarity of 2, where you have plus and minus. So that is called as Zwitter ion. Now, due to the Zwitter ion form, amino acid actually shows an amphoteric behavior. So when that is the reason why they can react with both acids and bases. Clear? So they can react with both acids and bases. Right. Now, if you may go back and check here, I have marked some of them as stars here. So whatever the star marks which I marked, correct? These are all, essential amino acids which body can't produce, which our body can't produce, but we have to get it externally through the food source. Okay, mostly dal, chawal, and everything, vegetables, whatever we eat, they all will have these proteins. Okay, clear. And notice, I'll just put it as a note here. Note here. Okay. So if you could just remember one part of it, like essential, you can name that rest of them are non-essential. So that is why remember it like this. His, Leu, leucine, ILE, isoleucine, LYS, that is lysine, MAT, methanol, PHE, phenylalanine, THR, tyrosine, TRP, tryptophan, valine, and arginine. These are the ones which are essential amino acids. If I know the essential amino acids, it's easy to figure out what are non-essential. Clear? Right. So they usually exist in Zwitterian form. Next thing, okay, solubility, solubility of amino acid depends on pH of the medium. The pH of the solution, is higher or lower or anything. Depending on that, it will always start showing different solubility. How that happens, I'll explain that mathematically. Okay. Second, amino acids are, amino acids are crystalline. They are generally crystalline in nature. They have high melting point due to Zwitterian form. High melting point due to Zwitter ion existence. Correct? Right. So before going further into details about how this solubility is affected, what are the other conditions? First, let us quickly browse through the preparation reactions for amino acids. So first, amination of alpha halo acids. Okay. So this is amination of alpha halo acids. What does that mean? So first I need to make this into suppose let me write down this as a reaction which we are aware of. If you have RCH2COOH and this has been treated with X2 in the presence of red phosphorus. If you may remember, we call this reaction as HVZ reaction. We learned this in carboxylic acid. Okay. Through HVZ reaction, we know that we get this as RCHX COOH. Correct? If by chance I react this with ammonia in aqueous medium, you will get this as RCH. It will replace this X with NH3, I mean NH2, and here it will form a salt CO minus and NH4. And then again, if I hydrolyze it, you will get this ammonia coming out of that position and making this salt back into acid. So this is how you'll get alpha amino acid. So what we did is an amination of alpha halo acids. Okay. So anywhere if you have it like this, suppose if you have COOH here, even if you have a methyl here, so I require at least one alpha hydrogen. So X2 followed by red phosphorus followed by aqueous ammonia followed by hydrolysis. So in that case, what do we write? We will write this as methyl here, NH2 here, and COOH here. So this is an alpha amino acid. Please check quickly. Please quickly check it out from here to here. Right. See the next reaction. Gabriel thalamide synthesis is something which we are aware of and we've been using that reaction for a while now. So let me just recall that reaction again. See, uh, basically we make this from we make this from phthalic acid. Okay, so how do we make it from phthalic acid? So first we take phthalic acid, COOH and COOH. We react that with ammonia. So first it forms a salt which is CO minus NH4 plus, CO minus NH4 plus, and this on first heating we will get an amide, double bond of NH2, double bond of NH2. We call this as thal thalamide, thalamide. One second, thalamide. And further heating will actually make it into thalamide. That is, the nitrogen will be present here as NH and ammonia would come out of it. So now this will be called as thalamide. So what we get here is thalamide. This is the first thing we need to do. Now once you get thalamide, from here the actual reaction starts. So we react this with KOH to make this into N minus. N minus is a good nucleophile. So if only we react with some, chlorine substituted C double bond O ester, something like OR here, like this. Okay, some ester. It could be any ester. So in that case, this minus would go and attack here, attack on this carbon to remove the chlorine via SN2 mechanism. So we shall get this as double bond N connected to CH2 C double bond O OR with double bond O and double bond O. And on this, if you perform hydrolysis, there are two things that will happen. First, hydrolysis happen on this end also, which will convert this into phthalic acid. You know? Second, that nitrogen will convert into NH2 connected to CH2 and then C double bond of OH plus ROH. So the product what we got here is, you can see this is glycine, isn't it? An amino acid which is glycine. Okay. So if you want any other amino acid, all you need to do is keep this, instead of hydrogen, you keep one substitution here. And that substitution will help it formation of glycine form. Okay. So check out quickly, everybody. Clear? Next. The next reaction is about one minute. The next reaction is about um, Strecker synthesis. Okay, so what is Strecker synthesis? See, Strecker synthesis is synthesis from aldehydes. That is, if I take an aldehyde R CHO, okay, and first I'll react this from first I react this with ammonia in the presence of mild H plus, okay, so mild H plus, then followed by HCN addition, so that we can get first we'll get this as C double bond O or double bond NH, and after that HCN addition will give you cyanide here like this, correct? And once you get this alpha amino cyanide, then on hydrolysis you'll get this as RCH NH2 here and COOH here. This is also very useful in industries where if you want to synthesize some little bulkier alkyl, then Strecker synthesis is more useful because in this case you have to strictly follow SN2 in Gabriel Thalhamide synthesis. So we cannot have too much bulkiness around this position. Okay, but here that is not a problem because it is an addition reaction. Okay, so that R being little bulkier also does not make much difference. Here everybody, this is Strecker synthesis. If I want to show step by step, the first step is like this: RC double bond O NH formation, and after that addition will give you RCH and with cyanide followed by NH2 formation. Okay, thereafter on hydrolysis, cyanides are getting hydrolyzed to acids. Then now, what are all the chemical reactions you will notice? So first, amino acids when you react with NaOH, correct? So typically it's like an acid-base reaction. So I'll get this as RCH with NH2 and COO minus. Okay. And similarly, if at all we react this with dry HCl, if you react this with dry HCl, it will give you NH2 and COO ethyl like this ester formation. Lithium aluminum hydride will reduce this part into formation of NH2 and OH. Okay, clear? Sorry, CH2OH. NH2 and CH2OH. Next, alkylation. Alkylation is when you have CH and this will become NH, CH3 and this COH will remain. HNO2, diazonium salt. So that makes it CH and OH here and COOH because after removal of N2 plus water will attack through it and you'll get this as alpha hydroxy acids. Alpha hydroxy acids. Next, with HCl. With HCl, it will get protonated and you'll get this as NH3 plus and COOH. With PCl5, it will become RCH, NH2 and acid chloride. It will become acid chloride. Same goes with SOCl2 also. It will become acid chloride, COCl. Okay, very simple, straightforward. I mean, all repeated reactions. So you can please check it out. What are all the reactions we are getting? Please check everybody. Okay, guys. Let me repeat the properties again. Check out. These are colorless solid crystals, high melting point. Once again, let me finish. So this is colorless crystalline solids. They possess high melting point. Okay, due to electrostatic attraction due to Zwitter ion. In solid state, amino acids exist as Zwitter ion. They are soluble in water or polar solvents, insoluble in non-polar or ether solvents. Solubility depends upon the pH where amino acids exist as a Zwitter ion that shows the maximum solubility. Okay, next pH exists when the amino acid is shown as the Zwitter ion, and if the composition, remember that if the percentage composition of the amino acid is mainly in the form of Zwitter ion, then we say that pH of the solution is isoelectric point. It is called isoelectric point. And at isoelectric point, amino acids only move to either anode or cathode direction. Okay, amino acids will only move to anode or cathode direction. Clear? So this logic we should know. Getting stuck in the door. Yeah, keep it open. Yeah, it's okay. See, next. What is the calculation of this, isoelectric point? Okay, it's a very important deal. For an amino acid, this is how it exists. Correct? This is the amino acid it exists. Clear? So what we can say, for this to exist, right? We can assume that initially this was an acid. Imagine this is an acid. Why this is acid? So here the H plus can come from ammonium side also. H plus can come from acid side also. So which clearly suggests that we have two. Okay, I'll give it. So you have two types of hydrogens that can be lost. And now this is definitely more acidic. So that is the first H plus which will be lost. So the first ionization of this acid, we can call it as with an equilibrium constant Ka1. And once this is formed, this can also still behave like, acid, because this NH3 plus, okay, so this NH3 plus can also be able to give one more H plus onto it. So if it gives that H plus, then you will get NH2 here and CO minus here, correct? So it is a very similar uh, working of how the dye acids work. Okay, table. Okay, it is like a dioic acid uh, ionization. Okay, so now the pi, that is the isoelectronic point, would be the somewhere in between these. I mean, this is what you need to get as a more composition. If this composition has to increase, the forward direction dissociation should increase, backward direction dissociation should decrease. That will keep most of the solution in this form. When that exactly happens, that happens exactly at the uh, average value of pKa1 and pKa2. It happens exactly at the average value. Okay, to to make you understand this logic, let me take you through the ionic equilibrium working one more time. Okay, let me take you through ionic equilibrium working. Best example is if you have HCO3 ion. Okay, I'll get it. I'll get you. For example, HCO3 salt, sodium bicarbonate salt. Now let's say its concentration is C1. Okay, And we know that HCO3 minus has ability to ionize also. It can give H plus and CO3 2 minus, which we call it as Ka2. At the same time, HCO3 minus can react with water. It can hydrolyze in water and convert itself into H2CO3. I'll write it down here. H2CO3 plus OH minus. These two reactions would happen. This is called hydrolysis constant. Okay. And Kh value. And second thing what you'll notice is that whatever the H2CO3 is forming, that will again be in dissociation with HCO3 minus plus H plus. So this is Ka1. So literally when you take HCO3 minus, that is sodium bicarbonate salt in water, you will notice these three equilibriums exist together. Hai. So in that case we can say Ka2 will be defined by definition as H plus concentration into CO3 2 minus concentration upon HCO3 minus concentration, while Ka1 is HCO3 minus concentration into H plus concentration divided by H2CO3 concentration. So what if I multiply Ka1 into Ka2? Check properly. So if you notice that this HCO3 minus is getting cancelled, I will have H plus whole square into CO3 2 minus concentration upon H2CO3 concentration. Now this is what happens. See, the first dissociation is also very weak here. Ka2 is very weak, and at the same time KH is also very weak. Hydrolysis is also very weak dissociation, and second dissociation is very extremely weak. So we can always assume the fact that carbonate ion and H2CO3 concentration, if they are equal, that means maximum existence is present in HCO3 minus only. Neither this would be present in large quantity, neither this will be present in large quantity. I'll get it. So Ka1 into Ka2, that will be equal to simply H plus square. So if I take the Pa value, pH value, that will be pH is equal to half of pKa1 plus pKa2. So now let's apply the same logic here. That is, if at all I want to increase the concentration of HCO3 minus, or rather to keep this concentration high, in that case, this one and this one should be extremely low concentration and ignorant. Correct? That is the same logic you apply here. That is, to increase this concentration, neither this, which is like a hydrolysis form, neither this, which is a dissociation form, the both should not be in a large quantity. Both should be equal quantity and small amount. In that regard, then the Pi value, that is isoelectric point, will be averaging of pKa1 and pKa2. So please notice this. Relate with the derivation ones. Check out quickly. I'll give you a minute's time. What has been noticed is when it comes to different R groups. Okay, so check this R group. Okay, if this R group is hydrogen, methyl, phenyl, isobutyl, butyl, all of that, right? Those are all neutral amino acid. So when they have usually neutral amino acid, in most cases, right, the pi value was found out to be close to 6. So it is very close to 6. Clear? Next, if it is OH, somewhere OH present, that is 309. Okay. Uh, if you have any of those kind here, CONH2 kind, aspartame, asparagine, or uh, what do you say, glutamine. If you take those cases, their pi value is close to somewhere 5.5. And by chance, if there is at least one acid group present, extra acid group, pi value will drastically change to 2 or 3. And by chance, if you have NH2, it will drastically change toward 8 to 10. And histamine is a special case, its pi value is exactly 7.6. Alright, its pi value is exactly 7.6. Alright, now let me show you this with an example also here before I start solving the questions here with all different cases. I want to realize this with an example. Suppose, for example, let me call this neutral amino acid like this. That is NH3 plus CH2 COOH. This is glycine. And this part of the component form, let us call this as A. And it is going to give you pKa1 to form this as NH3 plus CH2 and COO minus. And let this be B. And then it will be in equilibrium with pKa2 to form NH2, CH2 and COO minus. Let this be C. Okay. You know, for glycine, the pKa1 value is given as 2.3. pKa2 value is given as 9.6. Okay. Now tell me when pH is equal to 1. When pH is equal to 1, which one will be major quantity? Because this dissociation is hardly observed. This is the no chance, which means major quantity that will be present will be only A. You'll hardly see any B or C, correct? Similarly, if you have pH value as 2.3, at 2.3, A and B will be in equal amount, correct? So neither A will be complete, C is completely 0, A will be half, B will be half. Okay, right. Next, if pH is equal to 8, in this case, if pH is equal to 8, it is B. And then if pH is equal to 9.3, what if it is 9.3? Got it? Not 9.3, I'll say it as, hmm, I get, wait. If pH is equal to, how much is the average? Let me check out the average. 9.6 plus 2.3 by 2. Okay. So that is 9 and 11. 11.9 by 2. So which is 6.95. Close to 7. Okay. Now listen to this. Which means anywhere between 2.3 to 9.6. The major quantity will be always this one only. Clear? So if you were asked that what is the major quantity present, you will say only Zwitterion. This will be present, that will be minor, this will be minor. In what range? Between 2.3 and 9.6. So this will be major, rest 2 will be minor. So I'm not writing this as only, okay? But if it is pH is equal to, uh, let's say 11, okay? 9.6 or 11. At 9.6 also, correct? B still will be dominant. B will be dominant. B will be dominant. And at pH is equal to 11, then C will be dominant. Because now you are kind of crossed that barrier here. So that means most of it gets ionized. So that will be making it C as the dominant form. Correct? Graphically, if you just recall the way we sketch it for pH, when you have to check out with respect to volume of NaOH, how do we draw the pH value here? This is how it is happening. See, first it is going almost like this. Then the first equivalence point will come. Then again it is going like this. The second equivalent points will come. And then the third equivalent will come. Let's see, I'll give you. Okay. So at this position, this is a point, correct? This is the point when we say A is almost equal to B. That is a buffer form, correct? So this is a buffer solution, correct? Similarly, this is also a buffer solution when B is equal to C. Okay, B will be almost equal to C. Clear? Okay, sorry. This is the point. B is equal to C. Yeah, correct. And this is a point where there is only B. This is the pH where it is only B. Clear? And this is a point where there is only C. Clear? And this is a point where there is only A. Please check. These are the respective pH values. Here I made a mistake. This should be B equal to C. Sorry, B is equal to C. Yeah, that is okay. Please check. Right. Now, please go through it once quickly. Check if you have understood how I plotted which is major and minor. Right, everybody look into this question. It's not that difficult. Uh, a decapeptide molar mass is given. Okay, so it could be some decapeptide. So 10 amino acids are there, and 10 amino acids implies that there are 9 connections and 9 water molecules out. So total weight of amino acids together will be equal to 796 plus 9 times of 18, correct? Because this much is the water lost actually, plus 796. So that makes it 958 grams is the total weight. Out of this total weight, 47% is only contributed by glycine. So percentage glycine will be equal to 47 by 100 into 958. So 47 into 958. Uh, so I'm getting this as 45.026. Okay. This is the weight in grams what glycine is contributing. What is one molecule of glycine is its molar mass is CH2, COOH and NH2, correct? So if you see total there are 24 plus 32 plus 14 plus and 5 nitrogen hydrogens we have. So that makes it total 75. Got it? Clear? Oh, sorry, this is 450, not 45. 450.26 grams. Okay. So which makes it how much? So 450 divided by 450.26 divided by 75. So that makes the number of glycine uh, amino acids. Glycine amino acids implies 450.26 divided by 75. So that is coming out to be 6. So that should be your answer. That is how many glycine units are present in decapeptide is 6. You're not able to see. One second. Let me reshare that. So here you can see the total weight of the amino acid is 958. Percentage glycine is 47 by 100 into 958, which is 450.26. One molecule of glycine is 75 grams. I mean, 1 mole of molecule. So number of glycine atoms will be 450 by 75, approximately 6. Check. Done. Right. Let me show you one more question. One second. Right. Please check this question now. This I'll add it to your notes. The question goes like this: total number of distinct naturally occurring amino acids obtained by complete hydrolysis of this molecule. So this was a molecule given, and I need to, hydrolyze it and try to figure out how many number of naturally occurring amino acids are present. Okay, so check this out. So here, for this case here, where do we break the molecule? So you can see this is an amide linkage. This is also an amide linkage. So wherever there is an amide linkage, you keep breaking it. So you can see I break, break, break here. Okay, and then we have break here and break here also, here, and here. After breaking all of this, can you see this side and this side? What are we getting? We are getting two glycines, 2 moles of glycines. And here we have acid with this group, and the same group we are getting here also. So 2 moles of this group we will get. And then you can see this group, this group, and this group. All three are exactly same only. So I will get 3 moles of this amino acid. And here also, if at all I break it here and here, I will get this group as well as this group here, correct? Is it? Yeah. Here also you'll get this as amine form here. So I think I made one mistake here. This should be directly connected. This was directly connected like this. Okay. So I broke it here and I broke it here. So again, I'll get 2 moles of glycine and this would become NH2. This entire thing will become NH2. So now I got total moles, 4 moles of glycine, 2 moles of this compound and 3 moles of this compound. But if you have noticed one thing, this is not a naturally occurring amino acid. Neither this is a naturally occurring amino acid. So the only naturally occurring amino acid is glycine. So answer is only 1. Okay. So because it is asked distinct number of natural amino acids. So answer is only 1. So guys, clear on this part? Right. Okay. So these are the type of questions that will be asked to you. Okay. So the next point is all about understanding the structure of protein. This is a very small part. Okay. So what I'll do,